Hi, it's Mr. Benson here with the video that I promised going through the electric power practice SAC. I'll try and get through this fairly quickly, but might have to split it into a couple of videos. The sound quality is not great, partly because it's raining and you can hear that on the roof, and there's something weird going on with my microphone. Onwards. Okay, so starting off with understanding magnetic field lines around a magnet. Now, like I said, this is probably a little bit better, this practice SAC, than the original one, because I'm specific about the number of field lines that you need to draw. Now, what you need to have here is the field lines coming out of the north pole of the magnet and coming around to the south pole of the magnet like that, going clearly from north to south. And the only thing that you really need to make sure with the field lines is that they don't cross each other. So, anything kind of like that is an acceptable answer. So that's your 2 marks there for the field lines. So question 2, if a compass is placed at point P and the magnetic field from the magnet is equal to the Earth's magnetic field, draw an arrow at point P to indicate the direction of the compass needle. So what you've got to think about is, at P, where is the compass's magnetic field? Sorry, where is the magnet's magnetic field going? So at that point, roughly, the magnet's magnetic field is a line that is going straight into the south pole of the magnet like that. So that's a terrible mess. But the important thing you can see from this is that we've got now at P 2 vectors. One of them is the Earth's magnetic field, which we know is just going straight up. The other one is the field line from the magnet, which is going directly to the left. Now, if we add these 2 vectors together, then what we get is something like this at about 45 degrees. Excuse my wobbly lines here. Now, then we're going to move on. Question 3. Now, question 3, so it's referring back to question 2. It says there is an electric current flowing in the wire below the magnet from left to right. Explain the effect that the magnetic field will have on the wire at point Q. Now, this is a bit of a trick question because it will have no effect. And the reason for that is that the magnetic field is at 90 degrees to the current, or the current is at 90 degrees to the magnetic field. So in any situation like that, there will be no force produced. Okay, question 4. A 20 centimeter wire is moved through a magnetic field of 0.15 Tesla at a certain velocity, and we're given the length. We're given the length of the wire and all that sort of stuff. So all this is just an induction question, and you've just got to think about the formula. Now, I'm pretty sure this is not on the formula sheet, so this is one that you need to have on your cheat sheet. So basically, it is just that the induced EMF is just the velocity times the magnetic field strength times the length. Now, the length must be in meters. So if you do stuff in centimeters, you're going to get the wrong answer. So we've just got 7.2 times 0.15 times 0.2, and that gives us an EMF of 0.22. Now, everything up here is the 2 significant figures, so that's what I can do. So my answer is 0.22. Okay, now this question possibly confused people because the way I laid the diagram out is a little bit unclear. But if you think about pretty much every electric motor question you ever look at, you have 2 poles of a magnet, a north and a south pole, on either side of the coil. Now, they don't have to be permanent magnets. They could be electromagnets, and that's what I've sort of tried to show in this idea here. That we've got these 2 coils, and we've got to think about where the fields are going. Now, this is requiring you to think about your grip rules. So you use your right hand grip rule to get the direction of the magnetic fields first. Now, these 2 coils are oriented the same way, so the fields are going to be going in the same orientation. Now, the current is flowing in this direction because remember this is the positive terminal and that is the negative terminal of the cell, which means the current is flowing up the coil like that. Now, if we do our grip rule, so you put your thumb in that direction, your fingers are going to be curling around, if you imagine where that wire is going, around the outside, around the front, like that. Now, if we continue going up to the coil like that, then your fingers are going to be curling around like so. And so the magnetic field is flowing up over the top of the coil, and then it's going to be going over like this and flowing in that end, like so. Now, the other one's going to be much the same, so it's out of that end, around, and into this end. Sorry, these are emails coming in making loud noises. So what can we say about this? Well, this must be the north end of the magnet, and this must be the south end of the magnet, north and south. Now, we know that when we put two magnets together and orient them like this, their fields start to interact with each other. So some of the north field from this magnet is going to, from the right-hand magnet, sorry, is going to be going through to the south pole of the other magnet, something like that. Now, this is giving us our direction of the field at point Y. Now, although I didn't ask you to draw this, you would also have some field lines that would be going from one to the other like that. So what this means is that the field at Y is actually going from right to left, which is quite important later. And the fields on both the coils are going basically coming out the left side and going in the right side. So the north pole is the left-hand end of each coil. Okay, explain the direction of rotation of the motor. Now, basically all we're doing in this case is we're referring to the right hand slap or force rule. But the problem is we need to be specific here. Otherwise, you're just saying a rule and basically, you know, trusting that the examiner believes that you know what you're talking about. Now, that's not okay. I don't think that that's a reasonable thing to do. So you need to actually justify things a little bit better by being specific that the current is into page, the field is right to left, and so the left side of the coil is going to, in this case, it is going to be pushed up, and in that case the rotation is going to be clockwise. Okay, calculating the force on the coil. This is something that is pretty straightforward, because all you've got to do is F equals NILB. The number one error here is people were forgetting to put in the number of turns. So we've got 500 times 2.5 times 0.15 times 0.45, and we get 84 newtons. Now, one other thing that happened a lot in the practice SAC is people are forgetting significant figures, which as we're getting close to the end of the year, you need to be getting better at, not worse at. Now, if you look at this, every bit of information I gave you except the 500 had two significant figures. So my answer is going to be rounded to two significant figures. Now, just before we skip to the next page, the other thing I just want to mention about question 6. When you're talking about electric motors, the only concepts that matter are electric motor concepts. Don't talk about things like flux in relation to electric motors. That's in relation to generation, and so you're mixing the two things together when you shouldn't.